Our next topic investigates ARIMA models. ARIMA models are generalizations of the ARIMA models that we've been discussing, but these ARIMA models allow for a seasonal dependence in the time series. So the S in ARIMA is for seasonal. So to give you an example where this can occur, suppose that you're interested in the monthly sales for a particular company, and the January sales for this company may be highly dependent upon the previous January's sales from the past year. Similarly, maybe June sales are highly dependent upon the previous June sales from the previous years. Excuse me. And so ARIMA models now allow you to include that dependence, which basically has a significant lag difference. Okay, so let's take a look at these ARIMA models. They're structured in much the same way as regular old ARIMA models. So a model that only includes seasonal components looks as follows in terms of these ARIMA models. We have this AR operator. Rather than using a lowercase phi, now I'm going to use an uppercase phi to differentiate it from when we had a non-seasonal model. Also, take a look at inside this parentheses there. We have the B as we've seen before, but now we have that backshift operator raised to the S power, where S is the season. So if I had monthly sales data, S would be 12. We also have the differencing component as well. It's going to be raised to the capital D power to differentiate it from when we had a non-seasonal aspect. But notice also here we have this 1 minus B raised to the S inside of it. So if I were to take 1 minus B raised to the S times xt, so I guess capital D would be 1 in this particular case. Now my differencing looks like this, x of t minus s. So again, that's how we take into account this seasonality. So we take all this times x of t, and then we have the moving average operator, but notice now again we have b raised to the s power there. This moving average operator has an order of q to it, capital Q, and I should have said with respect to the AR operator, its order is capital P. Also take a look at the role that S plays in those operators. And then last we take this moving average operator times WT, where WT is distributed independent, mean is 0, sigma squared W is the variance, so white noise again. Now, if S was equal to 1, of course, then this would mean that we go back to the kind of model that we've been talking about before, this non-seasonal ARIMA model. Okay. Now, in a purely seasonal ARIMA model that I just showed there, the ACF and the PACF form have a very similar form to what we had seen previously for a non-seasonal model. The difference is that let's say the spikes in the ACF or PACF, meaning when we have non-zero values, those occur over lags H equal S, 2 times S, 3 times S, so as a multiple of S, your season, where the remainder of the lags tend to have autocorrelations and partial autocorrelations equal to 0 in between. There are exceptions that I'll talk about shortly. So similar to what we saw for a table in the past to help identify AR, MA, and ARMA models, here's that same table, but now, excuse me, we look at lags K times S for making that determination of cutting off to 0 or tailing off to 0 and so on. Otherwise, everything remains the same. So just to focus in on one particular kind of model, a seasonal ARIMA, a seasonal AR model with some season S. So again, if we have monthly data, S would be 12. The autocorrelation function would be equal to capital Phi1 raised to the H power, but at lags S times H. The partial autocorrelation then would be equal to capital Phi1 at H equal 1 and 0 otherwise. So in summary, we have this tailing off to 0 at lags S, 2 times S, 3 times S for the autocorrelation function, and we have this cutting off to 0 after lag S times H. After lag S. Now, we can have these ARIMA models also include non-seasonal components as well. So the way that we would state our model is as follows. In terms of symbols, ARIMA, we do the non-seasonal part first, so that we have the order of little p, little d, little q. And then we use a multiplication sign, even though we're not necessarily multiplying anything. Then we have the seasonal component using capital P, capital D, capital Q. And then in the subscript here, we have little s to indicate, well, what that seasonality is. And this is what our model looks like. The seasonal AR operator, the non-seasonal AR operator, differencing for the seasons, the differencing for the non-seasons, x of t, the moving average seasonal operator, the non-seasonal moving average operator, and finally your white noise. So you can see these models can be rather complicated. And basically then, when we now think again of the ACF and PACF plots for a corresponding model like this that has both seasonal and non-seasonal components, just put the non-seasonal ACF and PACF with the seasonal ACF and PACF and just kind of combine them. And that's what you get for those kinds of plots. And so you can imagine now when trying to identify the orders of the P and the Q, it can again become more complicated now. Okay. So how does one then examine this ACF and PACF to make decisions about what potential values should be for the P and the Q? Well, my recommendation for doing this is try to handle the seasonal component first of the model. That typically is easier. So first of all, one should actually take care of any non-stationarity issues to begin with. So non-stationarity problems can occur with respect to the seasons as well. So if I had, let's say, quarterly data, so I have S equal 4, non-stationarity in the mean would look something like this, where every fourth lag on the ACF plot would have very, very high values. That would tell me then that I need 1 minus b raised to the 4th power, that whole quantity raised to the 1. Okay. Once you get taken care of all the non-stationarity problems, and you can have non-stationarity both with respect to the season and non-season at the same time. Once you got done with that, now then try to figure out the values for your capital P, the capital Q. In other words, try to figure out the AR and MA components for the seasonal aspect. So what you might do is maybe start conservative, choose a capital P that's equal to 1, or choose a capital Q that's equal to 1, examine the corresponding residual ACF and PACF plots to determine, well, do other seasonal aspects need to be accounted for? Then once you feel as though that you've taken care of the seasonal aspects, now you attack the non-seasonal aspects. So you look for the order for the little p, the little q by looking at the residual ACF and PACF plots. Again, you approach it much in the same way that we've done in the past. Again, you might need to look at multiple models to figure out what the correct value should be. So we'll have some examples of actually going through the process shortly. Now these seasonal ARIMA models can actually become even more complicated. So in generality, well, I guess originally, or let me back up. In the last set of models, we had basically two AR operators. We had two MA operators. We had two operators dealing with, not necessarily operators, but two parts of our model dealing with possible differencing. These two parts were for the seasonal and non-seasonal. Well, just in generality, though, you could have more than one AR operator. You could have more than two AR operators. You can do the same thing for the moving average. You can do the same thing for the differencing as well. You might have, let's say, sales for the company not necessarily only depend upon, let's say, one January compared to the next, but maybe some other seasonality component to the sales of the company that you need to account for. So in generality, here's where you can have, let's say, M different AR operators, where I just was very general here and decided just to use the little phi here, even though I could have seasonality in it. You could have capital R different moving average aspects as well, and capital K different differencing aspects too. In our class, we will just simply focus on having one seasonality component and one non-seasonal component to our models. Okay, so let's take a look at some examples then where these ARIMA models can be very useful. This first example, we've actually seen this data before. It deals with sunspots. And the unique thing about this particular data is that the seasonality aspect is not something that we're used to seeing in terms of, like, say, monthly data, quarterly data. Instead, these sunspots have about a 10 to 12 year cycle. So the seasonality isn't necessarily a season in terms of what we think of as a season. And so from this plot, though, you can see that we have these 10 to 12 year cycles, and these ARIMA models have been used to account for that with respect to sunspots. We've also looked at the OSU enrollment data in terms of most universities. Essentially, we have 3 semesters during the year: fall, spring, summer. So the season is actually 3 in terms of what S would be. And so we are actually going to examine this in further detail later on in this set of notes. Now, before we get to an example, I want to bring up 2 comments. First, large estimated autocorrelations are often present around the seasonal lags. So for example, let's say we look at a PCF plot. So we have -1, we have +1 here. We have, let's say, lags. Here's 4. Maybe I have quarterly data. And so on. Now with this plot, let's say an AR1 with a season of 4 is where the data came from. So we would expect to have a large value there. That's large in some respect, and then have no other large values throughout. Well, it wouldn't surprise me though to see maybe large value, to see perhaps even non-zero values surrounding lag 4 corresponding to these partial autocorrelations. If I had, let's say, an ACF plot for this same model, we would expect that this that these autocorrelations would tail off to 0 in terms of multiples of a season of 4. And so I wouldn't be surprised to see something like this. And unfortunately, I made my tick marks too small, where, oops, it should be at lag 12. Let me actually do a different pen color so we can see this better. Well, unfortunately, my pen's not working. Let me try another pen. Well, unfortunately, none of my pens are working. When I'm trying to get it as, imagine at lag 4, lag 8, lag 12, we see that tailing off process with this corresponding ACF. Now, it wouldn't surprise me at lag 3 and lag 5, I also have some larger autocorrelations. Not as large as lag 4, but I would also have some larger autocorrelations there. At lag 8, I have this large autocorrelation because I'm tailing off, but also at lag 7 and 9, I have some little bit smaller autocorrelations surrounding it. So that's what I'm trying to get at with this comment here. Okay. Now, strong seasonal variation often causes large estimated autocorrelations at fractional multiples of the seasonal lags. What I mean by that is, let's say, let me actually see if I can pull up a different thing here to write on. There we go. Imagine we have monthly data. And maybe we have an ACF plot, again, for this AR1, but now the season is 12. It wouldn't surprise me, in this particular case, to have, here's 1, here's -1. Sorry, I'm getting to my point. That here we would have a tailing off as multiples of 12 corresponding to the ACF for this kind of a model. But at lag 11, lag 13, lag, let's say 23, 25. Maybe I might see something like this corresponding to my previous note. But at lag 6, I might see something like this. Also lag 18, I might see something like this, where I have also at fractional parts or fractional lags of this season, I also see these larger ones as well. Now, as we will examine very shortly, we can use a particular function R to actually see what the true autocorrelation function, the true partial autocorrelation function will look like. And you can see some of these properties that I'm trying to describe here. Okay, so let's move on here. Let's actually take a look at an example. So I've simulated some data from an ARIMA 0111. So here's P, D, Q. So with respect to the non-seasonal aspect, we have one difference. And then we also have a moving average component as well. Then with respect to the seasonal, I have one difference. And also I have a moving average aspect. The season is going to be 12. My data is in this particular comma delimited file. And here is my corresponding program associated with it. We're going to have 200 observations that were simulated from it. My variance is going to be 25, mean it's 0. There's theta 1, negative 0.4. Capital theta 1 is negative 0.6. Okay, so a very basic aspect that I might, for example, ask you to do with this kind of a model is actually write out the model so that x of t is only on the left side of it. And so this is what we have here. We have these two parts for the differencing. We have these two parts for the moving average aspects of our model. Then, to write it out so only x of t is on the left side, I move this seasonal differencing through with x of t. And notice what I get here. X of t minus x of t minus 12. Next, I move the non-seasonal aspect through as well. And so I get x of t minus 12 from the 1 part there. And then now I have a b there. So now when I take negative b times x of t, I get negative x of t minus 1. And a similar thing happens with the x of t minus 12. I get x of t minus 13. Okay. Now over here on the right side then, I move through the seasonal aspect of the WT. So that's how I get WT plus capital theta 1 WT minus 12. Then in a similar manner, I move through the non-seasonal aspect. You can see what the end result is. Let me do a little bit of erasing here because I'm making this a little bit messy. Next, I move all the x of t's, except for x of t itself, over to the right-hand side of my model, and there we go. So if one wanted to, let's say, simulate data from this kind of model, one could write a for loop that takes into account this structural form. Now also what we can do in R is that we can use this ARIMA ACF function that we've seen in the past to see what the ACF and PACF would be, the true ACF and true PACF would be for this particular model. Now we don't have a way to specify what the order of differencing is. We didn't have that before as well. So the ARIMA aspect of this model, let's say after the differencing has been done, we can see what the ACF and PACF would be for little q equal 1, capital Q equal to 1. Okay. But unfortunately, the function is not set up well to deal with the seasonal aspects of our data. So instead, to actually get this function to work for us, we're going to need to take these two MA parts of our model and multiply them out. So take this 1 minus 0.4 times b times 1. That's where I get this right here. Then take the negative 0.4 times b times the 1 minus 0.6 times b to the 12. And this is what I get there. Okay. So now what I have here are my coefficients that I need on b that I would normally represent in the ARIMA ACF function. But also what this means is that if I had, let's say, a b squared in there, I would have a coefficient of 0 on it. If I had, let's say, a b cubed in there, I would have a coefficient of 0 on it as well. And we need to actually represent that in the ARIMA ACF function because I don't have like an argument that says, okay, here's a seasonal component, here's a non-seasonal component. So this is how I can work with this particular function. Let me come over here to 10. Okay, I'm going to copy and paste that outside of what's actually in the notes right now. And so the first coefficient, the coefficient on b was negative 0.4. Now we have a 0 on b squared. We have a 0 on b cubed. We have a 0 all the way up to b raised to the 11th power. Okay. So because of that, I'm going to repeat 0 10 times. Then here's the coefficient on b to the 12th. Here's the coefficient on b to the 13th. I'm going to put this all, I'm going to combine this all together and associate it with my MA argument. And so here are the corresponding, here's the corresponding autocorrelations. Of course, we do not look at this lag 0 value, but here are the remaining autocorrelations going up to a default value of 14, and you can increase that using an appropriate argument in the function itself. Okay, let me come back over here. Now I want to do a plot to the autocorrelations. So for my y argument in my model, I'm going to put in the results from the ARIMA ACF function. And since I have seasonal data, I'm going to increase my lag that I'm going to look at to lag.max equal to 50. because if I have a season of 12, you know, it's going to take a number of, I'm going to be very interested in let's say lag 12, lag 24, lag 36, lag 48. And I want to see the pattern that occurs across those higher lags than what we had previously needed to. On my x-axis, I'm going to put 0 to 50. Remember, I'm starting at 0 there because that's, excuse me, that's what the ARIMA ACF function gives me first, is that lag 0 value of the autocorrelation. And here's the rest of the code there. Now I'm going to draw a line at h equals 0, and here is the ACF plot. So again, we ignore this first one. But what we see at lag 1 is we have that large lag. I'm sorry, that large autocorrelation in absolute value. Well, remember, we have this non-seasonal aspect to this particular model. It's a moving average 1, non-seasonal. And so this is what we would expect to have happen, where all the remaining ones would be 0 if I only had that non-zero, if I only had the non-seasonal aspect. Now, since I do have the seasonal aspect, what we should be expecting as well is at lag 12, I have a non-zero autocorrelation. And indeed, that's what I have happen. Now, as I mentioned previously with respect to the ACF, it's not unusual to also have right surrounding that lag 12 or that lag S autocorrelation to also have some non-zero autocorrelations as well. And you can kind of see why this happens by when we actually wrote out the model, and you can see the different, you know, it's not just, let's say, x of t minus 12 or w sub t minus 12. It's also, for example, x of t minus 13. That's why this occurs. Now, to do the, and so for a seasonal moving average with a lag of 12, with a season of 12, you know, what we end up having is a cutting off to 0. And indeed, that's what happens with the ACF. Now, with the PACF, we should see this tailing off to 0. And so to do the PACF, I do exactly the same set of code as before, but now I put the PACF equal true in there. And this is what we get. So the non-seasonal component, remember that should be tailing off to 0, and so this is what we normally have seen in the past. For the seasonal component, we should have a tailing off to 0 as well as a multiple of 12. So lag 12, lag 24, lag 36, lag 48. That's what we would expect to have happen. Also, because as I mentioned just a minute or so ago, you're going to have some non-zero values kind of surrounding the corresponding multiples of lag of 12 here. Notice what we have here. And again, this is completely expected. It's because of that formulation of the model. Now, to simulate data now from a ARIMA model, we can use ARIMA.sim, but it's not as easy as one would expect. And I'll talk about how to do that shortly, or actually in the next bullet. Similar to what we had with the ARIMA ACF function, we need to actually multiply out the corresponding AR and MA operators, include zeros in there for coefficients on B when they didn't necessarily appear in the model, and simply one can use then the list statement in ARIMA.sim to specify now the model as what we've done before, but with these additional 0 parameter values for phi1, for the phis and for the thetas. Okay. Another thing you could do, of course, is to program the model into R and use a for loop, much in the same way as we've done in the past. And another way is to use a user-written package that's set up to, let's say, more easily simulate data from a SARIMA model. And in fact, the ASTSA package corresponding to Shumway and Stouffer's book has a function called sarima.sim that is set up to do this process. I have an example of how to use that at the end of my corresponding program for this example. Now, in the past, I've actually simulated the data. I've simulated observations from this particular model, and I saved those simulated values in a comma delimited file. And I'm going to use that data then for the rest of this example. When I simulated this data, though, I not only simulated 200 observations, I actually went up to 224. So I have 24 extra observations. So I have 24, let's say, future values. We're going to concentrate right now, first of all, on the first 200. That's what we're going to use to try to figure out what an appropriate model would be for this data. And then we're going to get forecasts from those using that 200 observations. And then we're going to compare those forecasts to what the actual true values were for the future. This is a nice aspect to working with simulated data, is that you can now assess how well this model would actually do in practice for what a time series analysis is meant for, to forecast. So I'm going to read in my data like I would normally. Here's the first 6 observations of my data. I'm going to pull the first 200 observations out of this data and put it into X. So next I can do a plot of my data like I would do normally. And this is what the plot looks like. Like I said, this is done in the exact same manner as I've done in the past. And from looking at this, we see this bouncing up in the series that seems to happen maybe every 12 data points. Also, we see this this trend that's going down. So we have non-stationarity in the mean. But to emphasize then this bouncing up or bouncing down behavior that we have every 12 points, let's redo this plot so that the grid lines help us to see the seasonal aspect better. And so this is what I did. So here's my plot function. For the X argument, I'm going to use X. Notice I'm not going to have a Y argument here. Then I'm going to also include an XAXT equal N value, which says for my X-axis tick marks, do not draw anything. In fact, do not draw any numerical values there, because I want to have a little bit more firmer control of those values, as you will see shortly. I'm going to plot then the corresponding points as well, make them in blue. And now I'm going to make this x-axis the way that I want it to be. So with the axis function, side equal 1 tells R we're going to do the normal, where we normally have labels on the x-axis. That's what R refers to as side 1. And then I want tick marks at a sequence of numbers from 0 to 192, and we're going to go by 12. The reason being is because we have a season of 12. Also, and this is going to give me also a nice numerical label that says 12, 24, and so on. Also, on the same axis, I'm going to put some what are called minor tick marks in there, where I just want to draw a little line to help me see better what the in-between, let's say, months would be. And I'm going to go by 2s. Here's my size of the actual little line that's going to be drawn for the corresponding tick marks. And labels equal false means don't draw the numerical values corresponding to where I'm drawing these tick marks. So by me not putting labels equal false there, the default was labels equal true. And so then R automatically will draw the numerical values. For my, okay, so also then to draw grid lines, I'm going to draw them in somewhat manually using the AB line function, where I'm going to draw vertical lines at sequence from 0 to 192 by 12. And then for my y-axis here, I'm also going to manually draw in my grid lines too. And so this is what we get. So notice here I'm going by 12 on the x-axis, and we can better see that indeed every 12th value approximately seems to have a certain pattern associated with it. So the whole purpose of this demonstration is to show you that when you draw our normal old time series plot, it can be very useful to draw this plot in a way so that you can see the seasonal aspect better. Okay, so let's do now an ACF and PACF plot of the corresponding data. I'm going to use a lag.max command to increase the number of lags that are shown on the plot because I do have this seasonal aspect. So here's my ACF function that we've seen before. Lag.max is now going to be set equal to 50. Here's my PACF plot or function that we've seen before as well. Lag.max is equal to 50. So here's the corresponding plot of the data or of the autocorrelations, partial autocorrelations. Similar to what we saw with the plot over time, we see that we have some non-stationarity in the mean. And with this ACF, then that's represented by having these very large autocorrelations for the particular lags. These large autocorrelations take a long time to decrease. Now, something else to also examine here is that notice at lag 12, I'm a little bit higher. Lag 24, I'm a little bit higher. Lag 36, lag 48. The reason why that's occurring is because, remember, with our model from which the data is simulated from, I not only have a non-seasonal differencing that's going on, but I also have seasonal differencing. So I have two components to this non-stationarity in the mean, non-seasonal and seasonal. And the ACF plot shows that. Because I have the non-stationarity in the mean, I wouldn't even look at my partial autocorrelation function plot. Okay. So what the ACF is telling me is that I need to incorporate a 1 minus b to the 12th and also a 1 minus b. For demonstration purposes, let's actually just look at one of these orders of differencing at a time. So first of all, I'm going to look at 1 minus b, that non-seasonal aspect to the differencing. How do I do the differencing? Well, I just use the diff function as what we've seen before. Lag equal 1. Why is it lag equal 1? Because notice I'm only going back one time point. With this corresponding differencing, I'm doing first differences. Do the ACF plot, do the PACF plot. Now, with the ACF plot of these first differences, we still see that we have problems associated with the seasonality aspect of our model. We have these large autocorrelations that are happening at multiples of lag 12. So, as we would expect, this is what's telling me that then I need 1 minus b to the 12th power with respect to my model. I need to do the seasonal aspect of differencing too. Also with the PACF plot, I wouldn't look at that as well because I know I need to have differences. So again, why am I also doing the PACF plot too? Well, when I do the ACF plot, I typically also do the PACF plot at exactly the same time. Also, some other interesting things to look at the ACF plot here is that notice how we have these, off, let's say, multiples of 12 in terms of lag, we have some of these other kind of somewhat large autocorrelations as well. And this, again, just demonstrates that this is something that is often expected when you have a seasonality component. Okay. So now let's do the differencing with respect to the seasonality component. And so to do this kind of differencing then, I use the diff function once again. My data is in X. Now I'm going to put lag 12 there. And that's going to tell R I want X of t minus X of t minus 12. I'm doing first differences with these. Now, also I want to do the 1 minus b part too. So I put all this then within inside of the diff function. Diff x equal what I'm getting from my first differences for the seasonal component. Lag equal 1, differences is equal to 1. Now in the end, it doesn't matter which you do first, the differencing for the seasonality or the non-seasonality part. You'll get exactly the same thing. Verify that on your own. Go through the math to see that. Okay, so I'm going to put then the results from this into an object called x2. I'm going to do my ACF plot. I'm going to do my PACF plot. And this is what we get. Okay, again, ignore lag 0 on the ACF plot. And similar to what we saw with the true autocorrelations and the true partial autocorrelations, we have these patterns. Because I have a non-seasonality component for a moving average model, at lag 1, I'm going to have a significant autocorrelation. Then I should have it cutting off to 0 after lag 1. And essentially we see that if we ignore the seasonality term or seasonality lags in this time series. Here's where my my usual bounds are being drawn to do a hypothesis test corresponding to these autocorrelations. And we see that generally speaking, these autocorrelations are all within those bounds, meaning that I don't have sufficient evidence to indicate a non-zero autocorrelation. Now, at lag 12 here, now we see the seasonality part of our moving average aspect of the model. We have this significant value there. Again, after lag 12, at multiples of 12, I should have non-significant values, and that's what we see at about lag 24, lag 36, and lag 48 as well. Also, what we see here too, you notice that we have like a little bit of a significant one at a lag 11. Well, this corresponds to what I was saying before and what we actually had seen in the true ACF plot too. It's not unusual to have some larger autocorrelations surrounding that seasonality lag. Okay. Now for the PACF plot, what we would expect is that with respect to the non-seasonality component, we would be having a tailing off to 0. And indeed, that's what we have there. For the seasonality component, we would also have a tailing off to 0. So lag 12, lag 24 about, lag 36, oh, it's somewhere around there, and so on. And so we're essentially having that aspect come true here too. Again, for lag surrounding where that seasonality component is, we might have larger ones in absolute value, larger ones as well, and we have that occur here. That's not something to be concerned about. Okay. So now let's do a plot then of these of this difference data. This is what we get. The plot is drawn in the same way as what we've seen before, but now I'm working with the x2 object. And what we see is that we no longer really have non-stationarity in the mean that we had previously. Also, what we see here, we don't have problems with non-stationality in the variance. Now you might be worried, well, geez, that one really goes far away from everything else. Well, don't be too picky there, okay? That's a non-statistical way to put this. That, again, with respect to the non-stationality and the variance, we're looking for consistent trends across time. We're looking for large segments of our time series plot where we might have different variances than in other parts of the plot. Okay. Let's see. So I think I've talked about all that here. And so what we saw with the autocorrelations and the partial autocorrelations of the different series, that indeed this particular, we saw that this particular model seems to be appropriate. Now, the problem that you may have, as we've discussed also before, is that if you don't know that indeed that is a true model, it may be a little bit difficult to figure out, okay, when is this tailing off to zero? When is it cutting off to zero and stuff like that? So it's reasonable that there might be justification for other types of models associated with it. You know, perhaps using an autocorrelation of for the seasonal component of 1 or 2, maybe for the non-seasonal component, maybe of 1. And so because of that, then, how about we actually take a look at a different model to begin with in terms of actually estimating the model and going through the diagnostics. So suppose we look at this particular model here, ARIMA 010 by 011 season 12. So what this is acknowledging is that I need the non-seasonal MA term, but maybe I wasn't as sure about the seasonal MA term. Okay. And also, one reason why I'm approaching the modeling this way is, as I've also mentioned before, sorry to repeat myself, sometimes though when you are teaching, it is very helpful to repeat oneself just to make sure the students get the point. Often the way to approach working with seasonal data is to try to attack that seasonal aspect in terms of the MA and AR components first. After you've done all the non-stationarity issues, you've taken care of that. Attack the AR and MA components of the seasonality component first. Look at the residuals and let those residuals guide you in the direction of how to adjust your model further. Okay, so to estimate then this ARIMA model, here's how we can do it. I'm going to put my results into a mod.fit type of object. My data is in X. My order for the non-seasonal component is 0, 1, 0. So little p, little d, little q. Now for the seasonal component, now I have a new argument here for seasonal. And inside the argument, I need to put everything into a list where the first component is the order for the for the seasonal component. So this is capital P, capital D, capital Q. And then I can put for the seasonality, I can use the period argument to specify S. So I estimate the model and then I print off the results. And so this is, let's say, capital phi hat 1, negative 0.6447. Here is the square root of the estimated variance of capital phi hat 1 as well. Sigma hat squared W. Here is the corresponding AIC that we will eventually want to look at. Okay. Now to examine my model further, to do the various diagnostic measures, I'm going to use the examine.mod function that I had written previously, and I use this in much the same way as before. But notice also here I include max.lag equal 50. The reason being is because for the Jung-Box Pierce test, I do want to go out and look at a larger number of lags associated with it since I have a season of 12. Okay, so the output then that this function gives us is that here's my z test statistic value for doing a hypothesis test of capital phi sub 1, is that equal to 0 or not? And we can see that the p-value is extremely small, saying that yes, it appears that this is important to include in the model. Let's now take a look at then the results from the function in terms of the plots. Let me get my pen out. So I can look at my standardized residuals. Notice I have -2 here, +2 there as well. And we do have a few that are outside of -2 and 2, but not that many. And so I'm satisfied here that I don't really have outliers to worry about. Also on this plot, I don't see necessarily trends of positive standardized residuals or negative standardized residuals as well. So I'm happy with this first plot. Now for the ACF plot of the residuals then, at lag 0, of course, we just ignore that. Notice at lag 1, I do have a significant value there, indicating, oh, I might need a moving average term relative to the non-seasonality aspect. And to further emphasize that, notice how all the other autocorrelations are within our bounds at plus or minus 1.96 divided by the square root of n. Now, one thing that I don't like about this plot is that I don't have a way, because this plot's generated by the TS-diag function, I don't have a way to go beyond the default for the number of lags. So when I actually call this function, or my function itself, that max.lag can only be used corresponding to the Jung-Box-Pierce test. Unfortunately, I don't have a way, even if I wrote it in there and still use the TS-diag function, I don't have a way to specify a larger number of lags. So how could you get around that? Well, just create this plot of the residuals simply outside of the TS-diag function itself. So p-values for the Jung-Box-Pierce test, look at this. I have some problems here with autocorrelation. I have these p-values that are very, very small, indicating that indeed changes need to be made. Why is this occurring? Why is it occurring so soon there? Well, it's because of what we saw with the ACF plot of the residuals at lag 1. So estimated PACF plot, I wouldn't necessarily look at that because well, let me back up, excuse me. I would look at that, what we would expect to have occur, since I don't have that non-seasonal component for the moving average model. I would expect a tailing off to 0 starting at lag 1, and indeed that's what we have. All the other partial autocorrelations are within our boundary lines. Here's a histogram of my residuals. You know, it's definitely not perfect in terms of normality, but it's not really necessarily too bad. Looks like I have a little bit of a right skewness. You know, often what I focus on is I want this line to go through the middle of the top of the bars, and we see that sort of happening with most. I'm just having little problems there. The QQ plot, it really doesn't look too bad. Maybe a little bit of non-normality, the tails of the distribution, but it's, again, not too bad. Okay, let me make this a little bit smaller now. So, in summary, you know, the residual ACF and PACF show no more signs of a seasonality pattern. So that's good. And so what this is all telling me is that I need to consider this particular model where I added the moving average component to the non-seasonality aspect. So let's go ahead and estimate that model. So my code's exactly the same as before, but now I've added a 1 there instead. Here is little theta hat 1. Here's capital theta hat 1. So notice it says S in front of MA. I didn't mention that before. That says seasonal moving average, the first. Here is sigma hat squared W. Here's the corresponding AIC as well. And I can use examine.mod with this model. We can see here the p-values associated with tests, the test for significance for these corresponding thetas. The p-values are all very small, indicating that they seem to be important for our model. Let me zoom in now again on these plots. The standardized residual plot looks good. Again, I don't really see any outliers. I don't see any trends amongst these standardized residuals. Here's my ACF plot of my corresponding residuals. Ignore the lag 0. Hey, this looks good. All the ACFs, estimated ACFs, are within our dotted lines there. Look at the Jung-Box-Pierce test. This looks much better than what we had previously. I have large p-values all the way out to lag 50. My estimated PACF plot of the residuals, that looks good as well. Everything's within those border lines there. Here's my histogram of my residuals. We have maybe a little, some deviations from normality there. Now remember again, the data was simulated though assuming normality. So this maybe is an example of a case where you shouldn't be too picky about this kind of a plot, because we do know that normality is the underlying assumption for the WTs. My normal QQ plot doesn't look as good as the previous one, but it still is not too bad there. I think with respect to the histogram there, part of this deviation from the red line that we see there is that perhaps we have maybe too many classes, meaning too many bars on this histogram for this corresponding sample size to get really a good picture of normality. Compare this to what we had with the previous plot where we had a lot less bars. And so, what one could do is actually redo the plot, the histogram of the residuals, using a fewer number of classes. And that's what I did here. And what we can see, this is a plot of the same exact residuals. This plot doesn't look as bad as maybe perhaps the previous plot. Again, we have maybe a little bit of deviation right around there, but I'm okay with this. Okay, so now here's my final model. And so like on a test or project or any other assignment that I give you, you do need to write out then the model itself. And so here's the model in a, I guess, purely symbolic form right there. But you do need to write this model out like this, where I just put in the corresponding parameter estimates. I put the structure of the model there. And of course, you cannot forget sigma hat squared W, because that is a parameter that you're trying to estimate. Now notice how close these parameter estimates are to the corresponding values that were used to simulate the data. I used 0.6 to simulate for the non-seasonal moving average component. I used negative 0.4 for the seasonal. And so we're getting again what we would expect. This is an advantage of using simulated data like this for teaching purposes. Okay. Now, what if I didn't know what the model should be, before originally? It would have been reasonable maybe to investigate some of the other models as well. And that's something that you should try on your own and see where that would take you. Would you get to a model that was similar to the one that is truly correct, or would it take you to a different direction? But in the end, for all the models that you look at, then you look at the diagnostics, make sure the corresponding assumptions of the model are satisfied. And amongst those models that do satisfy the assumptions, let the AIC help you pick or help you choose one overall model to use. Okay, so now let's do some forecasting. So what we're going to do is look at forecasts for the first 24 time points into the future. Now that might seem like a lot, but in fact it's just 2 seasons with this seasonality component that we have of season of 12. So that's why I'm going that far into the future, so we can get a good idea of is this model doing well for the seasonality aspect. So to do these forecasts, I'm going to use the predict function again. Here's where I store the results from my model fit. N.ahead is going to be 24 now. se.fit equal true to help me find confidence intervals shortly. Put the results into for.mod for the lack of a better name. For.mod meaning forecast model. Okay, so again, for.mod returns a list that has 2 components, pred and se. Both of these components have a TS class associated with them. Here is x201 tilde and then the superscript 200. So negative 317.5528. Here is x tilde. Unfortunately, it's not writing. X tilde 224 with the superscript 200. Here's the corresponding standard error for that forecast error. So this is the square root of the estimated variance of x201 minus x tilde 201 superscript 200. And you can do a similar thing then for 224. I can find my, let's say, my predicted values from time equal 1 to 200, the same way as I've done previously when we've looked at predicted values. And I can find my corresponding confidence intervals also exactly the same way as what we had before. So just for emphasis then, here is x201. The upper bound is negative 307.1465 and the lower bound is negative 327.9592. Okay, so that's my 95% confidence interval. Now, as I mentioned earlier, when I simulated this data, I actually simulated 24 more data values beyond 200. So we know what the true future values are. And I'm very interested in seeing how well our model does in forecasting these actual true values. So these true values are stored in the X component of my data frame, ARIMA.data. And so I'm going to pull those out and put them into an object called x.extra. Now let's do some plots. So I'm going to plot my data like I would normally. I'm also going to take into account that seasonality aspect in my plot so I can better see what's going on. To plot my predicted values for time equal 1 to 200, I'm going to use the lines function. Also, I'm going to combine that with my corresponding forecasts. So this is for time point 1 to 200. This is for time point 201 to 224. These are going to be plotted in black on my plot. Excuse me. Also, I'm going to do my corresponding forecast. I'm going to do my corresponding confidence intervals as well. And then let's actually plot what the true future gives us. So with the lines function, I'm going to plot x.extra from time 201 to 224. These true values will be in blue. Lastly, I'm going to put a nice little legend on the plot. Excuse me. And so this is what we get. There's obviously a lot of stuff going on in this plot. So this is one of these situations where let's zoom in. That would be very helpful to better see what's going on. You can see the corresponding code in my program for how I zoom in. I use similar methods as in the past. Okay, so I'm starting at time point 190 and going up to time point 224. The red is what was observed. The black is the predicted or the corresponding future forecasted values. The blue is the actual future that was observed. And the green dashed lines correspond to the corresponding 95% confidence intervals at each time point. And so this is what we get. Notice the model seems to follow the trend that was actually observed prior to 200. And then take a look at how the forecasted values tend to follow what the true future ones were. And the true future values are all within the 95% confidence interval boundaries or limits. So this model seems to be working really well. It's doing what we would expect in this simulated manner. So this is great to see this. Notice also how these confidence interval bands tend to get wider as we go through time as well. Now, we've also talked about a drift term in the past. What if we actually estimated delta for this particular model? You can do that with ARIMA models too. And so that's what I did. To incorporate delta in the model, I use the same kind of code as what we saw before, where I add an xreg argument to my function. And this is what I get. Here's my delta hat. And look at that estimated, or the square root of the estimated variance. Quite high. Obviously, if one were to do a hypothesis test in this situation, is delta equal to 0 or not? One would conclude there's not sufficient evidence to indicate a delta that is not equal to 0. And so because of that, then, I really don't have a reason that I would want to include this drift term in the model itself. So that then concludes this first example dealing with these ARIMA models.